So the topic of this video is spectroscopy, in particular proton NMR, and there are a couple different layers at which we want to look at this. First of all, we want to say, what does NMR tell us? NMR, in particular proton NMR, tells us what's the main message we get from that, and that is connectivity. Okay, to remind you what we meant by that, let's look at this guy. The name of this is, actually you should name this, right? What's the name of that? Pause the video, please, and name it. Okay, good. I'm assuming you pause that for a couple minutes and name that, and this is 2-methyl propane. Pretend that that's an H and a Y altogether, okay? So these have exactly the same molecular formula. To give you a chance, an empirical formula, to give you a chance to practice this terminology, please tell me, what is the molecular formula for butane? What's the empirical formula? Okay. What's the molecular formula for this? Right? What's the empirical formula? C2H5. So you can see that this is all stuff that we've seen before. Are these two different than how? How do they differ in their connectivity? What's connected to what? Alright, so that's what we're doing here. That's lecture number 1 for proton NMR. Lecture number 2 is we're going to start to talk about how it does that. And specifically it does that because of the differences in electronic environments of the protons, the hydrogen nuclei, which is just a proton. It's the difference in the electronic environments of the protons Alright, we might say, well, what do you mean by that? Well, let me give you an example of that. A real dramatic example is this. Okay? Now remember, we may have drawn this like, you know, you've got that there, and of course you've got these lone pairs of electrons. If this is the electron cloud, what's the electron cloud of this look like? Well, it looks probably like that, right? Can you see a three-dimensional shape there, electron cloud? Alright, we might say that that is partially positive because it's bonded to an electronegative element, where that's partial negative, that's partial positive. And this, describe the polarity of that. This is nonpolar all the way, 100% nonpolar, right? Because it's two atoms that have exactly the same electronegativity. So the electronic environment of these two hydrogens is different. That's what I mean by electronic environment. Now this is pretty extreme, a pretty extreme difference, but something like this might not be quite so extreme. Just looking at propane, where I won't draw those, but you see that that hydrogen and this hydrogen are different. This is on an sp3 hybridized carbon, that's on an sp3 hybridized carbon, so they're pretty similar. But that hydrogen is on a carbon that only has one alkyl group on it. This carbon has got two alkyl groups on it. Right? So these two are different. And they're different in their electronic environments. Alright, now this could be really complicated, and I think virtually every textbook that talks about proton NMR spectroscopy gets pretty deep into how they're different and why that matters. It turns out what we're going to do with proton NMR spectroscopy is we're going to subject this thing to a magnetic field. We're going to calculate, not calculate, we're actually going to observe the spin of this nucleus flipping. And all that's, you know, interesting, really interesting to some people, but to us it's something that's, you know, useful for us to know that. But the most important thing for us is the difference in the electronic environments. Okay, and that's going to make it so that the textbooks can use the term shielding and deshielding, and that's going to make it easier or more difficult to spin or to flip the nucleus to flip that that hydrogen nucleus. Okay, but most important, it's different. They're more easier or more difficult to flip because of this. And I say more easy, more difficult, I'm talking about the strength of the magnetic field that's required to flip it. Alright, so electronic environments. And I don't want to say much more about that. we want to do say though, let's go back to this other example. Here's another term that I want to talk about is neighbors. Alright, and that's going to, sort of has to do with this different electronic environments. Okay, but a new term is how many neighbors do these guys have? And a neighbor, this is probably one of the most difficult terms here for spectroscopy. A neighbor, what is a neighbor? Well, to get real precise, it's going to be a really complicated definition. It's in your textbook, of course. But a neighboring, let's just draw it and approach this a little more qualitatively. A neighboring hydrogen is a hydrogen that's on a carbon which is bonded to the carbon on which the hydrogen of interest is. So the neighbor of hydrogen A, right? This is not a neighbor of hydrogen A because he's actually bonded to the same carbon. This is not a neighbor of hydrogen A. Okay? But he is, and so is he, because both of these guys are bonded to the carbon that is bonded to the carbon on which the hydrogen of interest is. Alright, and then there's one last term that we need to know about neighbors, and that is they are non-identical. So in ethane, with the previous definition I gave you, that would be, let's see, let's call these A and B, okay? B would be a neighbor of A, right, because it's bonded to the carbon, which is bonded to the carbon on which hydrogen A is. However, since they're the same, they're not considered neighbors. Okay, so I say non-identical. Neighbors are blah, blah, blah. And there's some important terms in there, one of which is they are non-identical. Alright, so we're going to practice that. Definitely practice that a lot. But I want you to get exposure to that term before we look at it. And I guess I also want to say that you really first need to get very good at doing alkanes before you do alkenes. Alkanes are much simpler than alkenes. Let me give you an example. Again, we're going back to the electronic environments. If the electronic environments are different, then they can be neighbors. All right? I said can be. Right? I know. Let's look at this. Okay. So what's the name of this? If you don't know the name, please pause it now and take a second and think about it. What's the name of this? Alright, it is 1-propene. Now your textbook may have that as simply propene. Why? Why is the 1 not there? I'm not even sure what your textbook's going to say that is. It is 1-propene, but how is your textbook going to name that? Maybe this, maybe that. Why? Is it disconcerting? I'm not going to tell you. I'll tell you in class if you ask me. Alright, so let's look back at this. Now, tell me, that hydrogen and this hydrogen, do they have the same? And this is a CH3, right? Do they have the same electronic environment? They're both terminal, right? They're both on the end, and they're both on an sp2 hybridized carbon, right? But is their electronic environment the same? And the answer is no. No, it's not, right? Because this is cis to a methyl group, and this guy is trans to the methyl group. Okay, so alkanes are really complicated, but it's not so bad to look at these guys. I'm going to circle that and consider the hydrogens that are in there. How many hydrogens are in there? There are 3. How many hydrogens are in there? 1, right? And you can see, I think, just by looking at line bond structures pretty easily, that these guys' electronic environments are pretty different. So when we talk about neighbors, we are going to broad brush some of it. We're going to start out with some very simple examples, and really you need to like the simple examples before you get into the difference between, say, alkanes and alkenes. These can be really tough. Okay, and the last two terms, sorry about that, the last two terms that we need to think about are shift, which oftentimes is given with a little symbol like that. Shift. Okay, and that's, I mean, we can talk about why shift is oftentimes down here in parts per million. Shoot, what does that mean? Alright, so it turns out that we might have 2 signals from 2 different kinds of hydrogens, and the shift is going to be, where is it on there? That's just what's meant by shift. Okay, and then finally, splitting. Okay. What is splitting? Splitting is when you get a single signal, okay, but this thing breaks up into like a triplet. Splitting equals 3, and the signal usually we'll call a group as a single signal. Okay? If that were true, what would be the splitting of this guy? Right? Or simply, you would say there's no splitting at all. It's not split. Okay? Everything's together in one. Alright, and splitting is directly related to the number of neighbors. So we talked about neighbors up here. Neighbors, and n plus 1 is your splitting. So we're going to find out the number of neighbors that we have, and then we're going to add 1 to it and say that that's our multiplicity. So if something has 0 neighbors, then it's going to be a singlet. If it has 1 neighbor, it's going to be a doublet. If it has 2 neighbors, it's going to be a triplet. And if it has 4,002 neighbors, it's going to be really messy. Okay, that is all I want to talk about in the first 2 versions of spectroscopy. Now let's get in a little more detail.